Brunhilde Y11. Okay, so your do now activity is on the board. So on a piece of paper you need to create a mind map of what you can remember on these three topics. So we have naming salts, titrations and Punnett squares. Okay, so in the middle you need to put what can I remember, and then different arrows to what you can remember about the three different topics. It would be good if you could write down each topic in a different colour just to make it more clear. On your assignment, when you submit it, make sure you upload the picture of your mind map to your assignment. Okay, so as we go through the lesson, you're going to do the assignment out ready next to you to work through questions as we go through the lesson. If you have any issues, make sure you type any issues on the Microsoft Teams chat. Okay, so the title for today's lesson is Naming Salts but Backwards, Titrations and Punnett Squares. Okay, so our noddy words or aim of the lesson is to be able to name salts backwards, so students will be given the reactants and you need to give the name of the products. We want to be able to describe the methods of titrations and understand how to use Punnett squares to determine offspring's likely phenotypes. So our keywords for today's lesson are salts, titrations, inheritance, heterozygous, homozygous, recessive and dominant. Okay, so we're going to start with naming salts but backwards. First we need to recap how salts are made. So we did this a couple of lessons ago. But when we have a reactions with bases, so metal oxides and alkalides, so acids and metal oxides react together to form salt and water. So you have an acid plus a metal oxide goes to salt and water. An example of this is hydrochloric acid plus magnesium oxide. So this can go to magnesium chloride plus water, or you can see the chemical formula there. Alkalis are soluble bases and can also react with acids to form salt and water. So if acid plus alkali goes to salt and water. An example of this is hydrochloric acid plus sodium hydroxide to give us sodium chloride plus water, or the chemical formula is there. So this also happens with reactions with carbonates. So acids also react with carbonates to form salts. So carbon dioxide and water and salt are all produced as results. Remember, when we have carbonates, they will always produce carbon dioxide. So an acid plus a carbonate goes to salt plus water plus carbon dioxide. An example of this is hydrochloric acid plus copper carbonate, which gives us copper chloride plus water and carbon dioxide. Or the chemical formula is there for you as well. Okay, so we're naming salts. We know that the first part comes from the alkali or the metal oxide or carbonate, so the sodium is from there, and the second part comes from the acid. So we can see sodium nitrate, we have nitric acid here. So we have hydrochloric acid, they'll always produce chloride salts. If we have nitric acid, they always produce nitrate salts, and the sulfuric acid, they always produce sulfate salts. Okay, so we're now going to work through an I do and redo example, and then you're going to have a go at doing some on your own. So for the I do, I don't want you to write anything down, I want you to be focusing on what I'm doing. For the we do, I want you to pause the video and write in the answers before I say the answers, and then obviously for the you do, you're going to be working through these examples by yourself. Okay, so we're going to start with naming the acid. So we know that the second half of the salt's name comes from the acid. So I'm going to circle the chloride. And if we can remember, we know that chloride salts are always produced from hydrochloric acid. So now I know that the acid must be hydrochloric acid, or HCl. Okay, so now I'm going to go back to the first part, which I know comes from either my alkali or my base or my oxide. Okay, so there's two options we could have here. Potassium hydroxide and potassium oxide would both react with hydrochloric acid to give us potassium chloride. Okay, so you can choose which one you want to write. So I'm going to go with potassium hydroxide. Okay, so we've got potassium hydroxide plus hydrochloric acid goes to potassium chloride and water. So the reason I knew this wasn't a carbonate is because we didn't have carbon dioxide as well. Okay, so moving on to the we do activity, we're going to do exactly the same thing. Okay, but I want you to pause the video in between answers to have a go on your own. Okay, so I want you to pause the video now and just read through and think about what we're going to write. Okay, so again, we're going to start with the acid. So I'm going to circle the second half of the salt, and again, I know it's a chloride, so it must be hydrochloric acid. Okay, and if I circle my first part, we've got a calcium, but if you notice, we also have carbon dioxide being produced, so I know it's a carbonate. So therefore, I'm going to write calcium carbonate. Okay, so now I want you to pause the video and spend 5 minutes working through the examples. Okay, so working through the UD examples by yourself. There's going to be a mix of more challenging questions and then some easier questions, okay? So pause the video now and have a go at the UD activity. Okay, so we're now going to move on to titrations. So we're going to first talk about what a titration is. Okay, so we've just learned that acids and alkalis can react together to form salts. So we can use titrations to calculate the volume needed for each. So this is a neutralization reaction. Okay, so with a titration, we know one concentration of one of the solutions, but we need to work out the other. So this is why we use titrations. So our main steps include to carry out our titration to determine the volumes of acid and alkali needed to obtain our salt, and then to mix the acid and alkalides in the correct proportions. Okay, but this time without the indicator, because we use our indicator to determine the concentration needed. So you can then dry out this to form crystal salt. So more that we can see that a titration is a process to determine the concentration needed for one solution when the other solution is known. So for example, we're going to look at an example where we know the concentration of alkali and we're trying to work out how much acid we need. Okay, so we're first going to start talking about the equipment we need. So we can see in the diagram a pipette. Okay, so this is the long thing here, this is our pipette. I'll get the laser pointer out to make it clearer. So up here, this is our pipette, and this is used to accurately measure out a certain volume of the acid or alkali. So this is normally the one that we know. The pipette filler is to use to pipette it safely. Okay, so in the a few years ago, people used to do this experiment by blowing into it. Okay, but obviously this is a health and safety issue now, so we use the pipette filler instead. We then have a conical flask, and this contains the liquid from our pipette. This is where the known solution, the known concentration of solution is placed here. And then we have our burette, and this is to add small amounts, okay, of measured volumes of one reactant to the other to work out the volume needed. Okay, so we're now going to talk through the method of doing this. Okay, so we're doing this, for example, of hydrochloric acid plus sodium hydroxide. Okay, so I want you to pause the video and write down what you think would be the salt and what else would be produced when doing this experiment. Okay, so you should have said that it would produce sodium chloride plus water, because we can see we have hydrochloric acid, which we know will always produce chloride salts, and our product is also water, and the sodium comes from the sodium hydroxide or our alkali. Okay, so first step is to use pipette and pipette filler to measure out a set volume of sodium hydroxide solution, and then we're going to add this to the clean conical flask, and this will be the solution where we know the concentration. Okay, so in this example we know the concentration of sodium hydroxide. We're then going to add a few drops of indicator, okay? And this indicator is going to show us when the reaction is neutralized, okay? So the beginning solution indicator color will be pink. So our solution is going to start off at pink. So when it turns completely clear, we're going to know that we have enough of our hydrochloric acid to neutralize the sodium hydroxide or our alkali. So we're then going to fill the burette with hydrochloric acid and note down the starting volume. We're going to slowly open the tap at the bottom of our burette and add tiny amounts of hydrochloric acid in at a time. Okay, we're then going to swirl our conical flask and look for any changes in colour. When we do see a change, okay, so when it does go clear, we're going to swirl it to make sure it stays clear, and this will be our end point. Okay, and we're going to note down that final volume. We're going to then repeat these steps a few times until we have a range of titration finals between 0.1 and 0.2 centimeters cubed of each other. Okay, this is really important because this is when it's going to be really accurate. From those really close points, we're going to then calculate the mean titer. Okay, so this will exclude any times we went round where they had a big difference, and the beginning one, because the beginning one's always to find a rough estimate of where it's going to be around. Okay, so we now have an activity. I want you to pause the video and label the different parts of equipment. Okay, so either burette, pipette filler, all those different things, and you also need to write down which what part is for which purpose, and then come back to the video. Okay, so pause the video now and have a go at labeling the image on the diagram. To check your answers, you can then rewind the video and fill in any parts that you didn't get correct. Okay, so we now on the screen have an example of our titration results. So as we can see, we have our titration, our end volume, our start volume, and our titer at the end. And then we have our rough, repeat 1, repeat 2, and repeat 3. Okay, so we're going to start with working out how we would find the titer. Okay, so we always minus the end volume from the start volume. Okay, for example, looking at number 1, our end volume was 24.6 and our start volume was 0, so I'm just going to do 24.6 minus 0, and this equals 24.6 centimeters squared. So this would be our end point, okay? So that's just in the top corner here. So I'm then going to work out the mean volume, and I'm only going to look at the ones that have a really close proximity again. So remember, it's between 0.1 and 0.2 of each other, and I'm going to use these. And you always need to remember to ignore the rough, okay? Because this is just to get an idea of how close it would be. So my mean, I'm going to add up the two values, because in this case there's only two values I'm using. So 24.6 plus 24.8 divided by 2, because that's the number of repeats I had, equals 24.7 centimeters cubed. Okay, so I don't want you to focus too much on calculating the end results. That was just an example of what we would do after. Okay, so we now have an activity. I want you to create an instruction manual of how to perform a titration. So on a piece of paper, or you could also use a separate Word document and upload that with your assignment to have a direction card of what you would do to find the concentration of hydrochloric acid to neutralise a given concentration of sodium hydroxide. So as you can see on mine I've done here, so I have my titration as the title. You will need, or this will be where I put my apparatus, and then directions. And it's going to be a step-by-step approach of how to work out a titration. Again, we're using sodium hydroxide and hydrochloric acid as an example. We need to remember to include what we would start with on our end product. So what salt do we end up with? Okay. So you can rewind the video to look through the steps, and also if you're up for a challenge, make sure you listen to what I've said about the colour of the indicator and what colour the indicator would go at the end point, okay? But that's not necessary, that's just if you want to challenge yourself further. Okay, so we're now going to move on to Punnett squares. Okay, so we're going to talk through Punnett squares. So a Punnett square is a grid used to show the possible combination of alleles and offspring after fertilization and sexual reproduction. Okay, so you can use Punnett squares to show what the phenotype of offspring is going to look like from two selected parents. Okay, so we need to understand some terms first. We're going to first look at heterozygous and homozygous. A heterozygous allele is when there's one of each type of allele in there. Okay, but a homozygous is when there's two copies of the same allele. So with recessive, the recessive allele is only expressed in the phenotype if we have two copies of the same allele. Okay, so if it's homozygous recessive, then we would see that recessive phenotype. Okay, but a dominant only needs one to express it, so it's always expressed. If there's a dominant allele given, the phenotype would be the dominant feature. Okay, so this can be either heterozygous or homozygous, and that dominant allele will be shown in the phenotype of the offspring. Okay, so now we're going to talk through how we can create Punnett squares. So we have 4 steps we want to follow. The first, determine the parental genotypes, and then we want to split the parental genotypes and put them around the edge of the Punnett square. And then we're going to work out the new genetic combinations for the offspring, and we can use these new combinations to answer our question. Okay, so we're going to start with an I do, and again in this you need to just focus on what I'm doing and don't need to write anything down, okay? If you want to, you can copy up the I do into your assignment afterwards, but you don't have to if you don't want to. Okay, so I'm going to start from reading the question and highlighting our key bits of information. Okay, so the inheritance of fur colour in mice is controlled by a single gene. Okay, so you have white fur, so I'm going to highlight white is recessive and is shown by an A, and our grey fur is dominant, which is shown by a big A. So 2 mice are heterozygous. We know both parents are heterozygous for the gene colour. We want to determine the probability of offspring mice having white fur. Okay, so we know that these ones will have to be homozygous recessive. So I'm going to start with step 1, determining our parental genotypes. Okay, so they're both heterozygous, so I know they have a big A. Let's go back to my pen. So I know that they have a big A and a small a, okay, because they have both alleles in them because they're heterozygous. So we have big A and little a for both of them. So I'm going to put these for step 2, I'm going to put them around our Punnett square. So again, big A, little a. Okay, and now I'm going to use the Punnett square to work out the new genetic combinations. So the first one, in the first box is going to be, because as you can see we're going down up, so it's A times A, so we're going to have 2 big A's. And then for the next one we're going to have A with little a, okay, and then again A with the bottom one, that's going to be big A, little a, and then 2 little a's. Okay, so now I'm going to write out what combinations I have. So I know that I have AA, that's one of mine. One of my combinations is AA. Another combination is a big A, little a. And my final combination is little a, little a. Okay, now I need to work out the proportions they're given in. So I know I have 4 different squares, so it's going to be a number over 4. Okay, so now I need to count how many big squares is showing AA. I can see on my grid only 1 is. So it's only 1/4 of a chance, or so 25% of a chance, for my offspring white fur, okay, to have dominant grey fur. Okay, now I'm going to look at another one. So I have 2 squares with big A, little square. So this is going to be 2/4 or a half. Okay, so there's 50% chance that my mice are going to be grey heterozygous. Okay, just like the parents. And then finally, look at these. I only have 1 square showing AA, and this is going to be my homozygous recessive white fur. Okay, and we can see we're looking for white fur. and the only way of getting white fur is to have 2 alleles. So when I know that there's only 25% chance of having white fur, or 1/4. Okay? So we're now going to do a we do example, and then again you're going to work on some examples by yourself. So again, I'm going to start with highlighting the key bits of information. So the fur colour of a litter of puppies is determined by a single allele. So we have brown fur, which is dominant, and that is given by a capital B, and our blonde fur, which was recessive, okay, and that's going to be a little b. So the male parent is homozygous blonde, and the female parent is homozygous brown. What proportion of puppies will be blonde? Okay, so we're looking for blonde. We know already that we're looking for 2 little b's. So now we're going to write down our male parent. So this is our homozygous blonde. So this is our male parent. He's homozygous blonde. So he's going to be B. Okay. And then our mum or our female parent is homozygous brown, which is going to be B. Okay, and I'm going to put them into our Punnett square. So we'll start with the father up here. You can always write father to make it clearer. And then our mother is here. Okay, and then we'll do exactly the same thing and cross them over. So I know I've got a big B and a little b. I've got again a big B and a little b. And then again I've got a big B and a little b, and again big B and little b. Okay, so now I need to write down the new genetic combinations I have. Okay, so the only one I have is big B, little b, and that is or 100%. Okay, so now to go back to the question, I want to look at the proportion that will be blonde. I know that if I want blonde, then I have to have 2 little b's. Okay, but I don't have this. So I know that there's 0% chance, or 0/4, that I'm going to have a blonde puppy. Okay, so I now want you to pause the video and have a go at answering some of the you do activities. Okay, so we have a few examples following the same, and then we have some further practice to challenge yourself. Okay, so after you've finished, I want you to come back to the video and we'll go through some more questions. Okay, but don't spend too long on them. Spend around 5 minutes having a go at the more you do activities and then come back to the video. Okay, so pause the video now and work your way through the you do activities. Okay, so now that we've had a go at the you do activities, I'm going to mark them on your assignment and give you feedback based on what you've done independently. Okay, so you now need to answer the review activity. So we need to answer, what does homozygous mean? What does heterozygous mean? What is meant by a recessive allele? And what is meant by a dominant allele? So pause the video and have a go at these questions. Okay, so for the first question, what does homozygous mean? You should have said something like, it has 2 of the same alleles, okay? So a homozygous genotype has 2 of the same alleles. A heterozygous genotype means that you have 1 of each type of allele. And what is meant by a recessive allele? So a recessive allele needs 2 alleles, or to be homozygous recessive, to be expressed in the phenotype, okay? So we need 2 of our recessive alleles, or homozygous recessive, for this to be expressed in our phenotype, okay? And then finally, what is meant by a dominant allele? The dominant allele will always be expressed if present, okay? So it could be heterozygous recessive, heterozygous dominant, or homozygous dominant. Doesn't matter either way, the dominant allele will always be expressed in the phenotype. Okay, so there's now some further questions if you want to challenge yourself further based. Okay, so success criteria for today's lesson is that you can name the reactants in salt production from given products. Okay, so this is naming salts backwards. So from the products that we had the salt and then the water and carbon dioxide, and then you can name what reactants produce those. You can describe the steps of titration, and you can use Punnett squares to determine offspring's phenotype. Okay, so I now want you to go back through the assignment and make sure you completed all the different activities, and then submit your assignment with the appropriate pictures of the task that you have completed. Okay, so well done today's lesson. Again, if you've had any problems, make sure you communicate through the Teams chat of anything that you don't understand. Okay, so well done and goodbye.